Our next application has a little more heft to it, and the student will readily be able to see applications to problems of weight and portent in the real world. The testing of new drugs, sera, vaccines, is big business, multi-billion-dollar business. And sadly, it's necessitated in part because of the discovery of new pathogens which spread virulently and violently. Here's a make-believe toy example to try to get the key ideas behind the setting. Imagine that one has a virulently spreading animal disease affecting fully 1/4 of the population, 25%. And naturally, we are worried. And so there's a scramble to develop a medication, a vaccine, a serum, a remedy. Let's say that 3 particular sera, creatively labeled A, B, and C, are tested for efficacy against this disease. And let us say that the following data are reported. So serum A was tested on, let's say, 10 cows. 10 were inoculated, and it was discovered on observation that none of those cattle fell ill. Serum B was tested on 17 cows, and after a period of observation, 1 cow fell sick. And serum C was tested on 23 cows, 2 fell sick and died. Now, of course, these numbers are much too small for applications in practice. We can't really get much confidence with samples of this size. But again, we are trying to settle ideas, settle concepts. And once we have these concepts firmly in place, we'll be able to extend them to realistic samples. Our question is this: is there any evidence that any of these 3 sera are efficacious? And of course, now we're given real data, and we are in search of a statistical principle. A student might feel that this is vaguely familiar, and of course she would be right. This is very much like the setting we had in the discussion of the hot hand phenomenon in sports psychology. And a very similar kind of test can be constructed in this setting. Here is the basis of a statistical test, the birth of a principle. Suppose we compare what happens to an unvaccinated control group of a size similar to that tested and ask, do we get statistically similar outcomes or do we get very different outcomes? So, to crystallize matters, suppose we are considering serum C. The thought experiment, the Gedanken experiment that is being put forth is the following. Consider 23 cows from the large unvaccinated group of cows. Observe them for a period of time. If at the end of the observation period 2 or fewer cows get sick, then we have results for the unvaccinated control group which are similar or better than those that were advertised by serum C. If more than 2 cows get sick, then the unvaccinated control group has worse outcomes. Our question then is, what are the chances that the outcomes for the unvaccinated control group in this thought experiment, this Gedanken experiment, what are the chances that the outcomes are as good as or better than those reported? We now have the basis for a principled test. Let's put some nomenclature, some terminology, some notation around this. So, what is the model? It's admittedly macabre. The idea is that each cow in an unvaccinated control group falls sick or not, falls sick with a chance of 1 in 4, a 25% chance, or avoids getting sick with a chance of 3 in 4. In other words, a cow falling sick or not in the general population corresponds to the toss of a fictional coin whose success probability is 0.25. Of course, this is a rather macabre and and cruel use of the word success, because success here means the cow falls sick and dies. Now, suppose we consider a control group of size n, because in our 3 sera we have different sizes of test groups. So let's try to do this in general for a group of size n. What we're dealing with is a sequence of n Bernoulli trials with success probability 0.25. We're looking at n cows and asking how many of those cows fall sick. In other words, we are looking at the accumulated number of successes, illnesses, in that group of n cows. And of course now we know that S sub n, the accumulated number of successes, is governed by a binomial distribution with parameters n, the number of trials is the number of cows in the group, and success probability p of 0.25, macabre to be sure, connotes falling sick. Okay. Now we want to compare the setting to what has been reported. So we're going to ask, what are the chances that in this control group we got results as good as or better than those advertised? Let's introduce a little bit of notation. Let uppercase B of n and k represent the probability that in your control group of size n unvaccinated cows, that k or fewer fell sick. That the accumulated number of successes is no more than k. Of course, by additivity, this is just a sum of the binomial atomic probabilities. If we add them all up, we get a Bn of k. Now, how does this work for the 3 sera at hand? For serum A, we are looking at a control group in our thought experiment of 10 unvaccinated cows. We want none of them to fall sick. For serum B, we are looking at a control group in our metaphorical experiment of 17 unvaccinated cows, and we are looking for 1 or fewer to fall sick. And for serum C, we are looking at a group of 23 cows, and we are asking what are the chances that 2 or fewer fell sick. Now this is a simple binomial calculation. We just plug it into the equations, and here come these answers. Numerically, the chance of getting results as good as that of serum A in an unvaccinated control group of size 10 is just over 5%. It's about 5.6%. The chance of getting results comparable to or better than that of serum B in an unvaccinated control group of size 17 is just about 5%, 0.05. And the chance of getting results as good as advertised for serum C is about 0.049. Now, at the high level, what the students should take away from this is that in each of these 3 examples, the chance of replicating or bettering what is reported is about 5%. It's not very high. What does this tell us? Now, if we think back to how we set up the hot hand phenomenon, when you look at illnesses in a control group, we're asking, is there evidence that the control group behaves statistically similar to my vaccinated test group, or is the statistical behavior different? What our data tells us is that in each of the 3 cases, there's only a 5% chance that the unvaccinated control group of the right size gives you results as good as or better than that advertised. The odds are not very high. And that suggests that each of the sera actually is doing something. The smaller the chance of replicating what was seen in a control group, the more the evidence for the functioning of the serum. And this gives us a slogan. The more unlikely it is for claimed positive results for a serum to be replicated in an unvaccinated control group, the greater the evidence for the belief in the efficacy of the serum. So on this basis, we believe that all 3 sera are reasonable, that they all appear to give us evidence that they are functioning. But our slogan gives us a bit more. The smaller the chance that we can replicate what is observed in an unvaccinated control group, the smaller the chance the more the evidence in favor of the serum working. Based on this argument, we would say that serum C, which has a 0.049 chance of getting its results replicated in the general population, is superior to, and there's more evidence in its favor, than serum A, which has got a 0.056 chance of having its results replicated in the general population. Of course, these numbers are so small that they don't practically make any difference. But the principle is telling us something about how to implement strategy. A student might look at this and say, well, that's all well and good, but this is really a toy example. You would not surely make decisions on healthcare based upon testing 10 or 17 or 23 cows or people. Assuredly not. But of course now we're going to have to scale this up to a suitable size where we have reliability in the sample, where we have statistical guarantees that the sample does something well. Here are a couple of questions. One, how big should the sample be before we get an adequate guarantee that we don't get a statistical fluke in our testing? Of course, this is really a million-dollar question. We really need to understand something about the size of the sample and how it's going to play into the game. A second objection the students might have is that the analysis assumed that 1 in 4 cows were going to get sick due to this new disease, that 25% of the agents were going to get infected. Now, how does one know that? Now, in a large population, it's not at all clear if we have that kind of data available to us. And in fact, in general, we don't. How does one get around this? Well, the answer to the second question is by trying to infer, at least implicitly, what P is by doing more statistical tests. And the way this is done, for example, in the testing of a new drug, is to compare individuals who are given a drug with another group, a control group of individuals who are not given the drug, but to make sure that there is no bias, no subtle psychological factor coming into play. You give both groups what look like the same pills, except that some of the pills are the drug and some of the pills are sugar pills. They're placebos. And by doing such a testing, one can in principle build upon this framework. We will come back to this.